What we will do today will be a revision of what we had done in all the last 11 sessions. Okay. So what we will be doing today will be a revision of whatever we have done previously. So I will try to summarize from the starting how we had proceeded with this course. Okay. So initially, when we started the course, we started with thermodynamics. So if we remember, thermodynamics is it gives us a macroscopic description of the system. So while the macroscopic description could be the the position or the momentum of the individual particles constituting the system, if we talk about macroscopic description, we can talk about the temperature, the pressure, which are the macroscopic variables that can define the system. So thermodynamics allow us to define the systems in terms of these macroscopic variables, and we can so these many of these variables are actually physically measurable. So that's how we define systems when we are talking about thermodynamics. So regarding thermodynamics, we dealt with the different laws of thermodynamics. While the first law gave us the definition of empirical temperature. So it said that when two systems are separately in equilibrium with some third system C, then they are also in equilibrium with each other. From there, we could get important state function. By state function, we mean that it does not depend on the path it follows to reach the state, but it is a function of that particular state, right? So it's not path dependent. So any function which is state function is actually not path dependent. And one such state function is the empirical temperature, and that definition comes from the zeroth law. And then we went to the first law, which basically is the conservation of energy, which says that if you have dq, if you suppose give dq amount of heat to a system, some amount of it will be used up to increase its internal energy dE, while the other part of the energy would be spent in doing some work. Okay, so if you have a hydrostatic system, in that case, this work done can be defined as PdV, right? Where pressure, P is the pressure and volume is V. So similarly, you can have different generalized generalized forces and generalized displacements in terms of which you can define your work done. So basically, this is what the first law tells us. And then we looked into the second law of thermodynamics, which tells us that no process is possible where the sole result is the complete conversion of heat into work. So if you take QH amount of heat from the source, some amount of it will be converted to work, but some of it would still remain as heat, and that would be sent to the sink, right? So you cannot have complete conversion from heat to work, right? And then another definition or another way of stating this law is that if you are extracting QC amount of heat from some colder object, in that case, you have to do some external work on the system in order to do this process. So no process is possible whose sole result is the transfer of heat from a colder to a hotter body, right? And from there, we could define the efficiency of the system. So you can define it in terms of, so if you have this heat engine, in that case, the efficiency is defined as W by QH, and that is always less than equal to 1. And then you can have, if you're talking about a refrigerator, where you are extracting heat from some colder object, and then you're taking it to a hotter object. So there, the efficiency is defined as QC by W, right? So how much amount of work has to be done in order to extract this much amount of heat. So these were the three main laws of thermodynamics. And then from the second law comes the concept of a Carnot engine, which says that a Carnot engine is an engine that is reversible. Okay. And so it is reversible and it runs in a cycle. And with all of its exchanges taking place between a source temperature and a sink temperature. And so here, if you look at the Carnot cycle, you'll see that this is a isothermal expansion that is taking place. Then we have an adiabatic expansion followed by a isothermal compression and an adiabatic compression, right? And so it says that no engine operating between these two reservoirs. So this isotherm is at TH, and then you have another isotherm at TC, right? So TH is hotter temperature, TC is the colder temperature. So now What this tells you is that if you have an engine which is operating between these two temperatures, TH and TC, some uh, particular pair of temperatures, TH and TC, no engine can be more efficient than the Carnot engine. So the most uh, efficient engine is the Carnot engine, which is the reversible one. Okay. And from there, we could define that for cyclic transformations, you can say that the closed integral of, or the cyclic integral of dq by t is less than equal to 0. Okay. So if it is reversible, in that case, it becomes, so in that case, you have dq reversible by t. And in that case, for a cyclic process, it becomes 0. Otherwise, it's less than 0. And if for some, so if the system goes from some state A to some state B reversibly, then you can define this parameter dq by t as entropy, the change in entropy. Okay. And from there, we get the concept of entropy. And it says that, so your this is the definition for the reversible process. Okay. And now if you have an irreversible process, or for any irreversible process, that would always be less than the change in entropy. So in a way, you can tell that this energy or the entropy of any isolated system always tends to maximize itself as it approaches equilibrium. So delta S is always greater than equal to 0. Okay, so it's equal to 0 if you have a cyclic process. And so it's a state function. So it does not depend on how we are approaching the state. It depends on the state variables. Okay. So that means from the second law, we got this state function of entropy. From the first law, we got a state function of the internal energy, and the zeroth law gave us the state function of temperature, or the empirical temperature, right? Okay, and then we saw that if we have to define how a system responds to certain value of pressure, certain value of temperature, certain generalized forces, uh, how to define it? Okay. So we can define it in terms of the response functions. So these are the specific heat at constant volume and constant pressure. Okay. And from there, you can also define the compressibility or the expansivity of the gas. Like here, it's defined in terms of, so compressibility is given as minus del V del P at constant temperature by the volume of the system. This is the isothermal compressibility. Similarly, you can define the expansivity, which tells you how the volume changes as a function of temperature, keeping pressure fixed. Okay, so these are the different response functions, which gives us an estimate of how the system responds to different external, or like different change in different thermodynamic variables. Okay. And this is important to remember that you can have adiabatic processes. So by adiabatic, you mean that there is no heat exchange involved. Okay. And in those cases, you can have such kind of polytropic processes going on, where you have PV to the power gamma equal to constant. Okay. And gamma would be the ratio of the specific heats. And then this is how the pressure, volume, and temperatures are related in those kind of processes. Okay. So we had discussed about all this in our, I think, first one or two classes. And then what we did is that from there, we understood that now we can define our system, or especially how the system approaches towards equilibrium in terms of different potentials. Okay, so just like we can say that when a system goes to stable equilibrium, it tries to minimize its energy. So similarly, depending on what is your system, you can have different types of thermodynamic potentials, and uh, that can tell you how the system is approaching towards equilibrium. So if you have no heat exchange in a system, and the system comes to mechanical equilibrium with a constant external force, in that case, you can define an enthalpy of the system. Okay, the enthalpy is given as E minus J into X, where J is the generalized force, X is the generalized displacement. So for a hydrostatic system, J would be so it's a sign convention. So J would be given as minus P, and then X is the change, X is the volume. So in that way, you can write for a hydrostatic system, H equal to E plus PV. Okay. And similarly, now if you have isothermal transformations in absence of any mechanical work, if you have a system which is under this condition, then you can define a potential called the Helmholtz free energy. Okay. And the system always tries to minimize the Helmholtz free energy if the system is under this condition. And the Helmholtz free energy is given by F equal to E minus Ts. Okay, E is the internal energy of the system, T is the entropy, S is the entropy, and T is the temperature. Okay. Similarly, now if you have isothermal transformations involving some mechanical work but at constant external force, then you define a Gibbs free energy, which is another potential, thermodynamic potential, and the system tries to minimize the Gibbs free energy as it approaches equilibrium. So in this way, depending on what system or what type of system you're talking about, you can define different thermodynamic potentials in terms of which you can explain the approach of the system towards equilibrium. Okay. And we saw that these are the four very fundamental Maxwell's relations that can, in a way, so why is Maxwell's relation important is that it helps us to relate uh, physically measurable quantities with quantities like entropy, which are not actually physically measurable. So if you have some system, you can measure the maybe a system of gases. You can measure the compressibility of the gas. You can measure the expansivity of the gas. You can measure the temperature, but you cannot measure the entropy of the system. So if you have to characterize the system or if you have to define the system, you have to define it in terms of some measurable quantities. So Maxwell's relations help you to set this relation between microscopic, the quantity is directly related to microscopic descriptions, which are not actually physically measurable in experiments, to some quantities which you can physically measure. So like here, and this is how you can use the different Maxwell's relations and the cyclic relations to start from some, maybe some, see, the del P del V at constant entropy. So if you have to measure these quantities, you can use the Maxwell's relations and the cyclic relations as shown here. And then you get to some factors or some terms. So you can express this in terms of this factors or terms, which can be measurable. So here you have volume, here you have the expansivity and the compressibility, which are measurable. So in that way, any quantity can be expressed in terms of measurable quantities. And there comes the major use of Maxwell's relations. So, and how one can define the Maxwell's relations? So one can define the Maxwell's relations starting from some potentials. So you have to remember that the potentials are exact differentials. So if you use that property, you can start from any thermodynamic potential, either the internal energy or the enthalpy or the Helmholtz free energy or the Gibbs free energy, and you can define, you can derive the different Maxwell's relations. So as an example, if you consider the internal energy, so from here, you can say that del U del S at constant volume would be given as T, right? And then del U del V at constant entropy would be given as minus of P. So if these relations come from this differential form of internal energy, and then considering that U is an exact differential, you can do so here, that means the order of differentiation does not matter. So what you can do is you can do a derivative of this term with respect to volume. And similarly, you can do a derivative of this term with respect to entropy and then relate both of them as equals because the order of differentiation does not matter for exact differentials. And that would give you this Maxwell relation. So similarly, all of these different potentials can be used to define the different Maxwell's relations. So I think we did all this in the second class. Okay. And then the second or third, I don't remember particularly, but this is how our course was proceeding. And then we saw that how can we use the Maxwell's relations? So we can use the Maxwell's relations. So one of the physical significance of these relations can be seen in terms of how we get to this Clausius-Clapeyron equation. So here I would not go to the details of derivations, but what you can see is that it defines del P del T, that is the slope of the pressure versus temperature plot to the the terms given here. So here L is the system length, and then you have sorry, system latent heat, and then you have the temperature of the system, and these are the volume densities. So you can see this is for a system which is changing from so specific volumes. So for a vapor to liquid transition, this is how you can define the Clausius-Clapeyron equation. Similarly, you can define it for a solid to liquid transformations, and this in a way manifests itself in the phase diagrams. So one such example was this, that if you look at some liquid, and then if you look at water, you would see that in water you have the slope of P versus T graph in this when we have this solid liquid transition has a negative slope. So this tells you that this is the representation, or so this is how the del P del T slope in a way shows how ice has a ice why ice floats on water, right? So it has a lower density. So this is what you can understand from the del P del T plot. So, and that itself manifests its so it has its manifestation already inherent in the Clausius-Clapeyron equation. Okay, so in that case you can consider this to be the specific volumes of liquid versus solid, right? And there you would see that you would get a negative slope for water, and which would be a positive one for the other liquids. So that's how it manifests itself in the different phase transitions and in different physical processes. And that's what you see in the phase diagrams. So then we used this information, whatever we had studied, to do certain questions. So I had just chosen some particular questions just for you to recall what we were trying to do. So if you look at the Carnot cycle, we could use, so any, so here you have this plot of pressure versus volume, okay? But similarly, you can have TS diagrams, TP diagrams, and how do you get to that is by remembering what kind of process each of these lines signify, right? So if this is a isothermal process, that means when you have T versus S, or T versus P, or T versus V diagrams, the this line and this line should be a straight line because the temperature remains constant in those processes, right? So that's why you have the straight lines in all these processes, as you can see. And then in the steeper lines, what you see here is that if these are adiabatic processes, so the entropy remains constant here. So that's why you see that here, this these are vertical lines, right? If you have a TS plot. But then if you have a TP plot, you have to remember how the pressure is changing in this processes. So if the pressure is decreasing in this processes, that means you will have a plot which has a direction like this, so that it moves from a higher pressure value to a lower pressure value while it moves through this process. And then you have here, there's an increase in pressure, right? So that's why it has a slope like this, right? So the concavity or the convexity of the plots would be, okay, one can guess or one can understand this from the from thinking about what kind of process each of these lines signify, right? So we saw how we can draw this different types of diagrams, starting from some knowledge about how the system or how the system is changing with during a particular process. And then this was some, so this is a very fundamental thing to understand and remember how entropy and energy is related to temperature, right? So dsde is given as 1 by T, right? And so how you get that is from the definition of, so if you use the definition of entropy in the first law, you would get dE equal to TdS minus PdV. And from there, you can find this relation, which tells you how entropy, energy, and temperature are related. And you can see that this tells you that the plot D is the slope of dE versus ds gives you temperature. So the inverse of that gives you 1 by temperature. So this is a very fundamental or very fundamental and very important relation that comes out of the first law using the definition of entropy, right? So in a way, what was done here is that one had to look at the different slopes during different processes, A, B, and C, and comment on the temperature. And it was seen that this tells you that dsDE is equal to 1 by T. So greater the slope, lower is the temperature. So similarly, we found uh, this order in temperature during this process. So what's important here is to remember how you get to this and what does it signify. Similarly, this was another question which taught us that if you have some free energy defined, how do you define the other thermodynamic parameters from there? So suppose if you have the free energy, the Helmholtz free energy is given to you, okay, then how do you find the internal energy? So what you have to do in this case is that you know the definition of free energy that is given as U minus Ts. So that tells you that the internal energy is given as F plus Ts, where F is the Helmholtz free energy, right? And then now, so in all this kind of questions, what you have to think of is the differential form of um, the given potential, right? So here you have free energy. So if you write the differential form, this tells you how you can define the different thermodynamic variables to the differentials, right? So this tells you that del F del T at constant volume is minus of entropy, right? So if you get the expression, so if you have F, you can do this derivative to find the expression for entropy. And that definition or that expression for entropy, you can use in the expression for the internal energy. So that's what has been done here. You have the expression for F, you find del F del T at constant volume, and then use it to find the expression for entropy and put it in this expression. And that gives you the value of the internal energy. So if you start with some other, so in case you were given some other potentials, you have to similarly think about what is the differential form and how you can relate it to some thermodynamic variables. And from there, use it in the expression of the quantity that you have to find, and similarly find that variable, find that quantity. Okay. So then what we did is we saw that depending on the type of processes, the heat exchange or the work done by the system would be different, right? Because these are uh, inexact differentials. So it depends on how you are reaching some particular state. It is path dependent. So depending on the process, your values of heat absorbed in different processes would be different. So suppose if you consider some ideal gas following some process, in that case, you can say that when it's an isobaric process, that is when pressure is constant, your N becomes zero, right? And then if you have isothermal process, you know that from the ideal gas law, so you can say that in that case, this N value is 1. So PV equal to constant, PV equal to nRT, right? And then if you have some adiabatic process, then it's defined as PV to the power gamma equal to constant. So gamma is given by Cp by Cv. And then if you have an isochoric process, your N becomes infinity. Now, depending on these values of N, you can see that now that the expressions of the heat absorbed is different. So if you write the first expression, so here what you have used is you have used the definition of Cv. Cv is given as du dt. So dq equal to du plus pdv. That gives you dq equal to Cv dt plus pdv, right? And then here you can have this different expression. This is just doing an integral, right? And what you see here is that now when n is not equal to 1, you get this expression. But when n equal to 1, you get a logarithm term, right? Because dv by v, integration of dv by v gives you a ln term. So that's how you define it for n equal to 1 and for n not equal to 1. And then if you put the corresponding values of n, you would get the expressions for different kinds of processes. So this is for isobaric process, this is for isothermal process. This is the case when n is equal to 1. Then you have isochoric process and you have adiabatic process. And you can see for adiabatic process, the heat absorbed is 0, right? So you have to, so given some process, if you are said what is the heat absorbed, what is the work done, and what is the heat that is incident, and how much of it is absorbed, how much of it has been used in some kind of maybe hydrostatic work or some kind of work, then you have to use this kind of relations to find the heat absorbed or the work done. And then we saw that the Maxwell's relations also help us in understanding how this response functions change with different thermodynamic variables. Like suppose if you want to see how the specific uh, heat at constant volume changes with volume, keeping the temperature fixed, then what you can do, you can start with this Maxwell's relations. And what this tells you is that now if you differentiate both sides with respect to t, keeping volume constant, and you can change the order because S is a state function. It's an exact differential. So if you interchange the order of differentiation, you would get an expression like this. And now if you multiply by T on both sides, TdS would give you, so you will have dq dt at constant volume, and that is what is Cv. So then what you get is del Cv del V at constant temperature is equal to T into del square P del T square. So this tells you that if you look at the double derivative of pressure with temperature, keeping the volume constant, that will tell you how the difference, the specific heat at constant volume changes with volume, right? So this is another physical significance of Maxwell's relations, which tells you how this kind of response functions changes with different thermodynamic variables. So similarly, if you start with if you start with a specific heat at constant pressure, then, and if you want to say how does it change with pressure, keeping temperature constant. So again, you have to start with the Maxwell's relations and then doing a differentiation with respect to temperature on both sides, keeping pressure constant. Okay, and then interchanging the, yes, and then interchanging the order of differentials, because that is possible because this is a state function. And that gives you how specific heat at constant pressure changes with pressure. And then given some expression for volume, you can use it to find del V del T or del square V del T square. And from there, tell how the specific heat changes with pressure. So these are some applications of Maxwell's relations and how they can be relevant in understanding physical processes. What we then looked at was that if we have some thermodynamic systems in stable equilibrium, what is the stability criteria? So what is the criteria that tells you, tells you how different quantities, different thermodynamic quantities change as a system approaches towards equilibrium. So we already know that a system tends to maximize its entropy or minimize its internal energy, right? So based on those, based on any of this, so either you can start with the required, what are the conditions required to maximize entropy, or what is the condition to minimize internal energy. You can find the difference, you can find the stability criteria. And what this tells you is that now putting the various values of generalized forces or generalized displacements, like here, if you have a hydrostatic system, you can consider J to be minus P and X as V. And then considering the conditions. So imposing the conditions like whether your number of particles are constant or not, volume is constant or not, you can find how this stability criteria manifests itself in in the changes in the different potentials. So this is the different stability criterias in terms of the different potentials. So how does the internal energy or the Helmholtz free energy or the enthalpy or the Gibbs free energy, how each of them change as the system approaches entropy. And we get all of that from the stability criteria, which comes from the fact that the system always tries to maximize its entropy or minimize its internal energy as it approaches equilibrium. So just as this is being done, similarly, you can use uh, the differential forms of different potentials and use these different relations to find all of these inequalities. Okay. So that was about thermodynamics. And then we moved to probability. So why did we go to probabilities? Because so when we talk about this macroscopic system, so we learned that thermodynamics gives us a macroscopic description, right? But in order to reach this macroscopic descriptions, we do not have to have the individual microscopic description of individual particles. What we need is a probabilistic description, which tells us that what is the likelihood that the particles will be in some microscopic state. So there comes statistical mechanics. So statistical mechanics is an inherently probabilistic description of system. So before we talk about statistical mechanics, we did a so as our course proceeded, what we did is we did a basic introduction to probability, where we learned what is a random variable, what do you mean by outcomes. So given some event E, what would be some event like tossing a coin. So there, what you get out of this event can be your random variable. And then whether it's a head or tail are the different outcomes, right? So similarly, you can define the random variables and the outcomes of your of your of depending on what event you are looking at. And what's important is that all probability distributions or values of probability follows this properties that it is positive. And then when you add the probabilities of two disconnected events, they should add up together. And then if you add the probabilities of all the different outcomes, okay, then the total probability should always, the summation of all the probabilities of all the different outcomes should give you one. So that is the normalization property of probability. Okay. And then we saw that we can define probability by a cumulative probability function, which tells you what is the probability that your your outcome lies between minus infinity and x, where x is your random variable. And then you can also define it in terms of probability density function, which gives you the probability of finding some element between or some outcome between x to x plus dx. So if you have cumulative probability function, it would always be a monotonically increasing function, while probability density functions can have a decreasing trend or an increasing trend. Okay, but what's important is it should be integrable. And then some function, if you have some function fx, where x is your random variable, and you want to find the expectation value of some function fx, then that can be done as an integration of p is your probability density. So px fx dx, that gives you the expectation value of function fx, right? So these were some basic concepts. And then we saw that this was an important thing to remember, that given the probability density function for some random variable x, how do we find the probability density function for some function of x, right? So here what was important to understand is that there can be multiple values of x that can give rise to same value of the function. So if you want to find the probability density of fx, you have to, that means you want to find the probability that fx lies between f to f plus df. Now for one value of f, there can be multiple values of x that gives you the same value of the function, that is f, right? So that's why you have to use the Jacobian, and you have to use this relation. So the probability density function for finding, which tells you what is the probability of having fx between f to f plus df, is given by this summation, right? Where this derivative is found at all those values of x equal to xi, which gives you fx equal to f, right? So this was a simple example which is based on this criteria. So then we talked about the moments and the cumulants. So given some probability density function, you can define a moment by this expression here. So it's the integral of px, x to the power n dx, that gives you the nth moment, okay? And the characteristic function is actually the generator of moments. How? So characteristic function is actually the Fourier transform of the probability density function. So if you have the characteristic function, you can see that that can be written. So if you expand it, that can be written in powers of k. And then the coefficients of the powers of k gives you the different moments, right? So that's how this is the generator of moments. Similarly, for if the PDF is about some point x naught, this is how you'll have a x minus x naught term. You get x to the power n when considering that x naught is equal to 0, right? And what you can then do is, if you take a logarithm of the characteristic function, you get a cumulant generating function, right? And cumulants are important because it's a very good way of describing your distribution. Like the first cumulant gives you the mean, while the second cumulant gives you the variance. Similarly, you can get the skewness or the kurtosis of the distribution from the cumulants. So if you have some probability density function, what you can do is you can do the Fourier transform on the probability density function to get the characteristic function, and a logarithm of that would give you the cumulant generating function. So because if you expand this now, the coefficients of all the powers of k would give you the corresponding cumulants, right? And you can also relate the cumulants to the different moments. That this is how that's being done. So the C subscript denotes the cumulants. Okay. So similarly, if you have some probability density function, what do? You do the Fourier transform, and then you look at the distribution in terms of the different powers of k. So if this is your distribution, you can tell that that means m1, the first moment is 0 because you don't have anything to the power k, right? And then m2, which is the coefficient of k square, is given as 2a square. So 2, because you have to look at this definition, right? You have to look at this definition. So you would have an 1 by 2 factorial, right? So that's why you have to multiply by 2, because you have no 2. So there is no 2 here. That means there must have been a 2a square term, which cancels with the 1 by 2 term that you get in this expression, right? The factorial term. So if you compare this expansion with this expansion, you would get the corresponding values of moment cumulants. And similarly, you can relate, because here the first moment is 0, or for the first cumulant is 0, that gives you m2, which is the second moment, as 2a square. So this is how you can find the different moments given some probability density function. Okay. And then we looked at some of the very common and very important distribution functions, like the normal distribution. So this is how the normal distribution goes as. And what you see is that you can define it in terms of the different moments. Okay, so normal distribution can be described by only two moments are required, in order to describe the normal distribution. And you see that the uh, so sigma here stands for the standard deviation. So sigma square is the variance, and the mean is given by lambda. If you have this distribution, here lambda is the mean and sigma square is the variance. So that's how you get an estimate of, so here the mean value is the mean of the distribution, while sigma square will give you the spread of the distribution. Similarly, you can have binomial distribution. So this happens when you have two outcomes possible, and as you can see here, it's a discrete distribution. This was a continuous one, but this is a discrete distribution, and from there you can define the different moments as given here. So here PA is the probability of getting the outcome A, PB is the probability of getting outcome B. So similarly, you can define the different moments in binomial distributions. And Poisson distribution is an extension of the binomial distribution. But now what you have done is you have subdivided the interval into a large number of divisions. Okay, so you consider that in one particular division, the probability of occurrence of one event is only one. So that is given by alpha. Okay, so alpha dt is the probability that an event occurs within some segment. Okay, and then q, that is 1 minus alpha dt, is the probability that no event occurs. So it's just that now whatever was pa here is given as alpha dt, whatever was pb is given as q, which is 1 minus alpha dt. And then now you have large number of segments. So considering that limit, that you have large number of intervals, you can use the same concept. You start with that characteristic function, and then you take dt tending to 0, which is another way of telling that your n, that is the number of subdivisions, tends to infinity, that you have large number of distributions. So that gives you this expression for the characteristic function. Similarly, you can find an expression. So you can do a inverse Fourier transform to get a probability distribution function in terms of x, right? And then write it as, so this expression tells you what is the probability that your m decays happen in some interval t, right? This is how the probability density function distribution looks like, right? And now if you expand it, so if you look at this characteristic function, right, and you take a logarithm and you expand it, so that would give you the corresponding cumulants, and you see that all the cumulants are constant, that is given as alpha t. So all cumulants of a Poisson distribution are same. So these are the different properties of the different types of distributions. These are the very common, very well-known distributions. So we had discussed all this. So you can use the concept that we discussed to find the moments for any kind of distributions that you have. So now that so after we had discussed about probability, we went to statistical mechanics. So we learned that statistical mechanics is actually a probabilistic description of your system, right? So what do you mean by that? Is that if you have some microscopic theory of matter, so suppose if you have particles moving, so you know the, so by microscopic description, you mean the position and the momentum of the different particles constitute the system. And then you have this macroscopic description where you talk about the temperature or the pressure of the system. But how do you connect both of them? There comes the statistical mechanics. Okay. So statistical mechanics helps you to derive the equation of states starting from some microscopic descriptions. So in a way, it allows us to obtain the macroscopic parameters like temperature, pressure, so on, from the microscopic details of the constituents. And in that case, we don't have to know the individual descriptions of all the constituting particles. We can just look at a probabilistic description of the system, and we will see how it works. So there, what it tells us is that if you have some system which is defined by some macro variables, right? And then because the number of macro variables or the state functions like energy, temperature, pressure, these are very small, these are smaller in number compared to if you look at all the variables that define the system in the microscopic description, right? So that means there will be a large number of microstates that correspond to one particular macrostate. So this fact that there can be multiple microstates that correspond to a single macrostate brings the concept of ensemble. So this tells you this, that now if you have n copies of a particular macro state, each described by different points in the phase space. Phase space is the, so you can define the phase space in terms of the momentum and the position of the different particles. So different points in the phase space corresponds to different microstates. But now, if you say that if you have n copies of the same macro state, okay, but then they are described by different points on the phase space. So dn for some value of, so here, like the momentum and the position at some t equals to the number of representative points in an infinitesimal volume in the phase space around some point, so point defined by the position and the momentum of the particles. And then what is the probability that you have this number of microstates in this phase space volume? That corresponds to some macro state. Some particular macro state is given by limit n tends to infinity dn by n. So this tells you that now if you want to compute the macroscopic values for some functions, you can do ensemble averages. So this is how you define the phase space density given some particular macro state, and an average over this ensemble. So how you do that is an integration over the phase space volume of this term, which is obtained by multiplying the phase space density with the observable. So that gives you an average value of the different macroscopic quantities, right? So that's how the concept of ensemble comes into picture. Now, in order to define, so what kind of phase space density should a system have, right? Given some uh, given some system. So what is the characteristics, what is the property of a phase of the phase space density that it should follow in order to have a system in equilibrium? So if you have systems in equilibrium and you have some macroscopic description, you want to find what is the corresponding phase space density that relates it to the microscopic description. How do you find that? So in order to find that, you have the important thing that one has to remember is what this Liouville theorem tells you. So this tells you that the phase space density in some phase, so around some point in the phase space, that behaves as an incompressible fluid. So that means that the phase space density is stationary with time. It's not changing with time, because if you have a equilibrium macroscopic state, that means your macroscopic state variables are not changing with time. That in a way tells you that the phase space density is stationary. So that means del rho del t is 0, and that gives you this relation, right? You get it from the Liouville's theorem. So this in a way tells you that now the equilibrium phase space density for any system should be a function of your Hamiltonian of the system, right? So now in the next slide, what I'll discuss is that it's also already been discussed in our classes, that now So there can be different ways of having different phase space densities depending on what kind of system you are in. But all of them, in all those cases, you will see that the phase space density is a function of the Hamiltonian, right? So for a microcanonical ensemble, for example, you see that, so this is you so you have a microcanonical ensemble considering that your system is a closed one. So there your energy is fixed. So you define the system in terms of energy and the different, you can say, the generalized displacements, right? So you can, for a hydrostatic system, you can define it in terms of energy and the volume of the system, right? So it's a closed system. In that case, you can describe it in terms of a microcanonical ensemble where the energy remains fixed. And there you have the equilibrium phase space density given by 1 by omega, where omega are the number of microstates corresponding to some energy, corresponding to this energy E to E plus dE, so that your system lies in this energy level. So omega is the number of microstates corresponding to this microstate, this condition, right? And for all other cases, it's zero. So how do you get to that is from the fact that your system always tries to maximize its entropy. So if in terms of that means that your system always tries to maximize the number of microstates corresponding to the given macro state. So the condition of maximizing the number of microstates would give you a particular equilibrium space density. And for a closed system, which is described by the microcanonical ensemble, you get that the phase space density is actually constant, which is given as 1 by omega. So if you use this relation, you can define the entropy as KLN omega. So once you find the number of microstates corresponding to the given microstate, you can find the entropy. Okay, and so that in a way, so KLN omega can be written in terms of an integral by the expression given here. So 1 by h to the power 3n comes from the normalization, and minus, so that means it's the average of minus KLN rho, right? So that's how you define entropy. And this is what happens when you have a closed system. Now, if you have a system where you can exchange energy, then you get a canonical ensemble. So you describe the system by a canonical ensemble. And what happens here is that now the phase space density is described as e to the power minus beta h by z, where z is your partition function given by this integral here. So again, here you can see that rho, the phase space density, is a function of the Hamiltonian. And this z, the partition function, has all the information that is needed to define the different, or that is needed to derive the different thermodynamic variables. Like you can find a potential, the Helmholtz free energy in by using this relation minus KT ln z. Okay, and then you can also use the partition function to derive the expression for internal energy, which is given as minus del del beta of ln z. And once you have F, you can use the differential form of F to define to find the various other thermodynamic variables or the equation of state. And then when you have a system, which is an open system where you can exchange energy as well as particles, there what happens is now you have this e to the power minus mu n term, right? So it comes because now you can exchange particles as well. And this is how you define the grand canonical or the macrocanonical partition function. And again, you can use the partition function to find this grand canonical potential, which is given as minus KT ln Z. So this Z here shows the partition function for the grand canonical ensemble. And you can see that the grand canonical ensemble is related to the canonical, the grand canonical partition function is related to the canonical partition function by the relation that we have here. Okay. So that tells you that if you can define the canonical function, you can just extend it using this concept to the grand canonical system. So in order to use, or in order to find the number of states or number of microstates corresponding to some ensemble, or in order to find the thermodynamic variables based on this ensemble theory, what was important and what we had discussed in I think our fourth or third or fourth classes was to find the volume of an n-dimensional sphere of radius r. And I'm not going through the details, but if you If you remember, what we did is that we did this kind of a variable transfer, and then we saw that the volume of an n-dimensional sphere has a form like this, where you have r to the power n, where r you can consider as, so this is your sphere. So your sphere has a radius of r. So you have the volume expression as r to the power n Cn, where n is some value which depends on the dimensions that you are talking about. Okay. And then when you use the standard Gaussian integral, what you can finally get to is the expression given here. So this gives you the volume of an n-dimensional sphere of radius r, right? And we'll see how, and if you remember, this was of great use in solving for the different density of states, or and then using it to find the different other variables, right? So if you consider an ideal gas in a microcanonical ensemble, so it's a free gas, free gas particle. So the Hamilton is defined as p square by 2m, and it's in 3 dimension. You have n particles, so nu goes as 1 to 3n. And so what you get here is that now if you do this integral, volume comes out. So because your Hamiltonian only depends on momentum, so you have this d3nq outside the integral given as v to the power n. But then now you have to find this integral. And this is actually a volume of 3n-dimensional sphere of radius root over 2me. So if you use the formula we were just talking about, this would give you this expression for omega. So where omega is the number of uh, microstates that can lie for h less than or equal to E. And then you can find the number of microstates corresponding to the particular energy that we are talking about by this expression. So you do a derivative with respect to energy. You have this 1 by sigma naught, which comes because of normalization. You would see that this is identified as HQ, right? And then you find an expression. So from omega now, you can find k ln omega to find the entropy. So this is your expression for entropy. But if you recall, this is not the correct expression, because it does not take into account the indistinguishability of the particles. So you are overcounting the number of microstates. Because the particles are indistinguishable, that means the numbering of the particles does not matter. And if you take that into account, you would have another 1 by n factorial that would come into the expression. And then the expression for entropy becomes this as given here, right? So this was this Gibbs factor that we had spoken about, the 1 by n factorial term. So for indistinguishable particles, the Gibbs factor has to be considered, while for distinguishable particles, we don't add the Gibbs factor. So this was your expression for entropy when you considered ideal gas in microcanonical ensemble. And similarly, when we went to canonical ensemble, what did we do? Now we first found the partition function, right? So here H is replaced by the Hamiltonian that is given here. That is the Hamiltonian for the ideal gas. Then we find the corresponding expression for uh, so you have this 1 by n factorial because of the Gibbs factor, and you solve it to find the expression for the partition function. So this is your expression. So this is your expression. You define this term h square by 2 pi m kt to the power half as lambda, which is the thermal wavelength of your system. And then this is the expression for n particles, n ideal gases in some volume V and in a system represented by some temperature T. So this is your partition function for that system. And now you can use it to find the free energy expression, the Helmholtz free energy. And if you remember the differential form of energy, you can use it to find the different thermodynamic variables like the pressure or the entropy or the chemical potential. And this is how it looks. And from there, you can also find an expression for the internal energy. So internal energy can also be derived directly from the partition function by using the relation that it's given as minus del del beta of ln z, right? So that's how, if you find the partition function, you can ultimately find all the different thermodynamic variables pertaining to the system. And then if you have a grand canonical system, what do? You know the relation between the grand canonical partition function and the canonical partition function. So only this term is the extra term that comes in, and e to the power mu by kt is called the fugacity of the system. So if you have identical non-interacting particles, so that means z of tvn, so that is the canonical partition function for n particles, would be equal to canonical partition function for one particle to the power n by n factorial. And if you use that relation, you can say that this is how the grand canonical partition function is related to the canonical partition function for one particle. So that means once you find the canonical partition function, you can extend it to find the expression for the grand canonical partition function. And similarly, you can find the macro canonical potential, which is given by this relation here. Then the macro canonical potential is again related to the different thermodynamic variables by this expression. So now the different differentials of this macro canonical potential will give you the different thermodynamic variables. And that's how you reach to the different thermodynamic variables. We saw that all ensembles, microcanonical, canonical, or macrocanonical, all of them, when we have large number of particles, so when n is very large, yields similar kinds of results, right? And then, so that was the description about the ensemble theory and how you use the ensemble averages or the concept of ensemble to link the, you can say, the thermodynamic variables in terms of the phase space density, which the phase space density is actually a representation of the microcanonical description. And then you relate it to the different macrocanonical variables like the pressure, temperature, and how do you do that? And that's what we just discussed in terms of the ensemble theory. Then what we move to is to understand or describe these systems in terms of density matrices. Because now if you think about a quantum mechanical system, it's always easier to define them in terms of matrices. And so there we brought in this concept of density matrices. So, and with the concept of density matrices came two terms. One is a pure state and one is a mixed state. Now, we saw that what is a pure state and what is a mixed state and how are they different from each other in terms of what are the properties of the density matrix, and how do they differ depending on whether your system is a pure one or a mixed one, right? So we saw that when you can define your system completely by one particular state, that is a pure state. And in that case, the density matrix is given by this outer product of your wave function or the state vector. But then if you have a probability, if you have a system where different microstates are possible with different probabilities, then it becomes a mixed state. And in that case, this is how your density operator looks like. So if your system is defined by some particular wave function psi, which is given by maybe this this description. So up and down are the different basis vectors, and this is how your system is defined. So you have a particular state which defines your system, then actually you are in a pure state. But now if you have your density matrix described by an expression like this tells you that you have half probability of being in up state, well, half probability of being in down state. So that means your system now it has a probabilistic description of being in different microstates, half in up state, half in down state. So this kind of description where there are multiple microstates that is possible, that becomes a mixed state. And we saw that if you look at the properties of the density matrix, the trace of rho square is a measure of whether your system is a mixed one or a pure one. For a pure state, rho square is equal to rho. That means trace of rho square is 1, while for a mixed state, trace of rho square is not equal to 1. So if you find the trace of rho square, where rho is the density matrix, you can tell whether your system is a mixed one or a pure one. So this was a particular typical question. So here the density matrix was given and you wanted to construct the density matrix in terms of a matrix form. So how do you do that? Is that now each of the density matrix is defined by, so if you have phi m and phi n as the basis vectors, this gives you the different density matrix elements. So now for this particular question, if you define the basis vectors as plus z and minus z, then this kind of inner products would give you all the different density elements. So rho 1 is given by this inner product here, and that comes out to be 3/4. Similarly, if you find the other terms, okay, you would get the corresponding density matrix elements. And so the density matrix turns out to be something like this, right? So now if you find rho square, you would get an expression like this. So the trace of rho square, as you can see, is not equal to 1. So this tells you that your system is not a pure state. Okay, so it's a density operator for a mixed state. What we saw here is that, so this was another typical question that tells you how one can move from one basis vectors to another, and how the description or how the matrix elements change once you change the basis, right? So suppose if you have your system already defined in this state, so that means your system is already defined by one particular state vector. So that means it's a pure state, right? And now you want to find the density matrix in the up and down basis. So what do? You do this inner product, okay? And this is your density matrix. Now, if you change the basis to this vectors given by the up plus down by root over 2 and up minus down by root over 2. So that is in the sigma x basis. Suppose these are your basis vectors. Now, how do the density matrix change? So what we do here is that we write this new basis vectors in terms of the old basis vectors, right? And you find the corresponding inner products as given here. Okay. And if you do that, you see that now the density matrix looks something like this. So here, as you can see, only one element of the density matrix is a non-zero one, which tells us it's a pure state, right? So similarly, so this tells you how the density matrix elements change once you go from one basis vector to another. So these were some of the very common and like this, we had already discussed these questions in details in the classes, but these are the basic concepts. So if you have some basis vector, how would you find the density elements, and how would that change under different under change of basis, and then what does it signify, right? What are the different what do the different terms signify? So if you find the trace of the density matrix with the matrix of some observable quantity like sigma x or sigma z, that would give you the expectation value of that particular observable, and that's what we get here, right? We find the expectation value of sigma x or sx or sz. And then what we next do is that, so that was a concept of the density matrix, which is important when we talk about the quantum mechanical description of systems, right? So now we consider, after that, we move to this the description where now we move to a quantum mechanical microcanonical ensemble, right? So when we talk about quantum mechanical systems, we have to understand in details what does distinguishability and indistinguishability mean. And we saw that when the particles are indistinguishable, the numbering does not matter. In that case, you can define so there's a so in by changing the numbering or the position of the particles doesn't change your microstate. And while in case of a distinguishable one, you have different ways of arranging the particles, right? The numbering matters or the positioning matters. So then the number of microstates would be different, right? So you have this weight factor that comes in these conditions. And then now, if you consider a large number of a large volume where the energy levels, so it's a quantum mechanical system now. So you have discrete energy levels and they're very closely spaced. So what you can now do is that you consider that epsilon I denote the average energy of some level, and gi is the number of levels. So it's the degeneracy of some particular energy level. Okay, and then there you have some particular distribution. So n1 particles in first cell, n2 particles in second cell, and so on, right? So that means we have to first find how many ways is the distribution possible. Okay, and we see that this distribution differs depending on the type of particles that we have. So there comes three different kinds of particles. One is the Maxwell-Boltzmann particles, which are distinguishable particles. Then we have so in that case, we have to consider the weight factor that comes because of the innumerability of the particles, right? But on the other hand, we can have indistinguishable particles, But even there, depending on whether the wave functions of the describing the particles are even or odd, you can have Bose, yeah, Bose gas, or you can say bosons, or on the other hand, you can have fermions, which follow the Fermi-Dirac statistics, right? So this in a way tells you how the wave functions that describe the system has it's directly related to how the particles are being distributed in different systems, right? And you see that depending on this kind of particles or what kind of particles you have, the the number of ways in which a particular collection of particles can be distributed in some energy levels changes. And you can see that given some number of particles Ni in some particular in ith cell of the spectrum, while Gi is the particular degeneracy of that particular cell, you can have different kinds of distributions. Like for a Bose-Einstein particles, so which follows the Bose-Einstein statistics, or like the bosons, you would have a description, you would have a distribution which follows this number, right? So this is how you find the number of particles for bosons. While for a fermion, that changes to this expression as given here, because now you can only have 0 or 1 particle in each of the energy levels, right? It follows the Pauli exclusion principle. Well, on the other hand, for Maxwell Boltzmann cases, now you can see you have this 1 by Ni factorial that comes in because of the enumerability, or that comes in because these are distinguishable particles. And then this is the final way of finding how the number of particles can be distributed under different energy levels for a Maxwell-Boltzmann case, that is for distinguishable particles. Now, depending on that, your expression for omega would change, and similarly, your expression for entropy would change, right? And if you want to find the equilibrium condition, then what you have to do, you have to maximize the entropy. And if you do that, you see that the most probable value of n, or the number of particles in some energy level, epsilon, is given by this expression here. And this A changes from whether the particle is a boson or a fermion or a or a distinguishable classical particle. Okay. So, and once you find the expression for entropy, you know how to relate it to the other thermodynamic variables. So with that, you can find an expression that relates the thermodynamic pressure with the, so here this alpha and beta are related to the chemical potential. So alpha is given as mu by kT, beta is 1 by kT, and you have A depending on, so depending on whether your system is a boson or a fermion or a classical gas. And similarly, you find the expression for the different. So for all those different cases, you can find an expression for the thermodynamic pressure and use it to find the expression for the equation of state as well. And if you remember from the grand canonical ensemble, PV by KT is given as ln Z, where Z is the grand canonical partition function. So in a way, you can use this relation to find all the different thermodynamic quantities, right? So then we moved to a quantum mechanical canonical ensemble, where we now want to find the canonical partition function, but now we are looking at the quantum mechanical description. Okay, and there you use this statistical weight factor that for uh, this has already taken into consideration how the particles are to be distributed. Okay, so as you see for a for bosons, this is given as 1. For fermions, is also 1, but obviously this Ne, which gives you the number of particles in a particular energy state. Now, for a fermion, you can see this is limited to 0 or 1. And then this is your statistical weight factor for a classical particle, right? And then we use that to find the expressions for uh, each of the different types of particles. Okay. And what you can do is that you can also extend it to the grand canonical partition function. So there you would have this extra Z that comes in, where Z is the fugacity of your system, right? So if you want to find the grand canonical partition function for Bose-Einstein and the Fermi-Dirac case, what to do? So the only difference is in the allowed values of Ni, right? The weight factor is 1 for all both the cases because both of them are for the indistinguishable particles. Now there, what you can do is for a for a boson depending on what are the values, possible values of n epsilon. So you can have all values of n epsilon from 0 to infinity, right? So these two summations can be written as a product of summations as given here, right? And each of these values n naught ni goes from 0 to infinity for Bose-Einstein case, while for Fermi-Dirac case, the possible values of each of these ni terms is 0 or 1. And accordingly, if you use that, this is your expression for Q, that is the grand canonical partition function, right? This is the expression that you get, right? And from there, you can define the Q potential of the system given as PV by KT. And these are the different values of A, which corresponds to the different kinds of particles. So this lies at the heart of how you can use the, you can say, the quantum mechanical description uh, based on the ensemble theory, and how you can extend it to quantum mechanical systems and find the different thermodynamic variables. So, so if you look at this definition of average energy or average number of particles, this is how average number of or the number of particles are defined as. So here, this term here, 1 by z inverse e to the power beta e plus a, this is the mean occupation number. And this mean occupation number obviously differs depending on whether you are fermions, you have fermions, bosons, or classical particles. As you can see, for fermions, this lies from 0 to 1, right? While for bosons, you can see as epsilon is close to mu, or you can say the chemical potential is equal to the energy level. So in that energy value, so there you can see that it maximizes, right? So you have this maxima, and that actually signifies the Maxwell-Boltzmann, sorry, the Bose-Einstein condensation that one can physically see in bosons. So one important thing is that one, obviously, if you have large volume where you can estimate or you can consider that the energy levels are continuous, so you can move from summation to integration. And then, so this is how you move from summation to integration. You have to consider the integral over the phase space volume. And then depending on how the energy depends on your momentum, your expression for pressure would change, right? So you have this d epsilon dp term, which takes into account the fact how energy depends on momentum. And if you suppose for a free particle, if energy is equal to p square by 2m, so you can find an expression for pressure. You can also find parallelly the expression for energy and relate both of them to get this expression. So this is for non-relativistic particles, massive particles, where energy is given as p square by 2m. While for, you can say, something like photons, or which are or maybe ultra relativistic particles, there you would see that pressure is related to 1 by 3 E by V, right? That comes from the fact that then the energy is given as P into C. So then we described about in details about the ideal Fermi gas and the ideal Bose gas. So for Fermi gas, you put A equal to 1. So if you look at this expression here, A is equal to 1, right? A is equal to 1 for the fermions. And if you put that, you can find an expression for the number of particles. If you change from the summation to integration, this is how it would look like. For non-relativistic particles, again, you can do a variable change from the momentum to the energy space. And then if you solve it further, considering beta E as your variable, finally you would get to an integral form like this, right? So if you use this like this expression, so whatever integral that you're getting here, if you change it, you can consider this to be a function, which is called the Fermi-Dirac function, and then you can use it to express the number of particles per unit volume or the pressure of your system, right? So here, G is the weight factor that arises due to the internal property or the structure of the particles like spin. And then this is how your uh, different thermodynamic variables look like. So what you see from here is that now if you move to uh, low densities, your yeah, so now if you move to low densities or when the temperature is much higher, what happens is that your N by V, right, that is given as small n, into lambda cube by g. This entire term would be very, very less than 1. There you can consider that your z is much less than 1, or you can think that f nu of z tends towards z. So this is the classical limit, and you will see that you'll get back all the classical results. While on the other end, if you are at the low temperature limit, the n lambda by g term goes towards infinity, and there you see that this is how the mean occupation number looks. Okay, so it's 1 when the energy is smaller than mu naught, and it's 0 for epsilon greater than mu naught, where mu naught is the chemical potential at t equal to 0. So this is how it looks like, and this sets a limit to the energy value beyond which your occupation number goes to 0. So now if you look at the integral for the number of particles, you can change the limit from 0 to the Fermi energy. So this is called the Fermi energy. Okay, and so Fermi energy is the maximum energy till which your mean occupation number is non-zero and it's equal to 1 when and at t equal to 0, and gradually it changes, right? So what happens is that so that means EF is equal to mu naught, which is the chemical potential of the system at t equal to 0, and then that sets a limit to your integral. If you use that relation, you would find that the Fermi energy is dependent on it depends on the number density by this expression. All the other terms are constant. So EF is proportional to the number density to the power 2/3. And then if you use the relation between pressure and energy, you would see that the pressure goes as n to the power 5/3. Right? Now, these factors obviously will depend on what kind of dispersion relations you have and what is the dimension of your system. So this was for the ideal Fermi gas. And what we understood from as we started dealing with the quantum mechanical systems is that n lambda cube is a quantity that can tell you whether you are in the classical limit or in the quantum limit. So when L lambda cube is much smaller than 1, that is when the temperature is much higher or the density is much lower, you are in the classical limit. While on the other case, when your density is very large or the temperature is very small, then you are at the quantum limit, and gradually as n lambda cube increases, you go towards the quantum mechanical regime. Okay, and quantum effects come into picture. So what we then see is that we then move to the ideal Bose gas, and here what happened is, so now you have put a equal to -1, and that gives you this expression for thermodynamic pressure and the number of particles. So here this tells you that for this value to be well defined, your z e to the power minus beta e should be less than 1, which tells you that now the chemical potential should be smaller than the ground state energy. Okay, so if you have free particles, mu should be less than 0. Okay, and that says a limit to z. The value of z lies between 0 to 1. For large volume where you can consider the spectrum is continuous, you can move to integration, from summation to integration. And if you do that, you would see you would get an integral like this, right? So again, depending on what kind of dispersion relation you have, you can get different expressions for pressure. So for non-relativistic free particles, you can define a density of states, and you would see that for three-dimensional three-dimensional case, particles, non-relativistic particles, where energy goes as p square by 2m, you would see that the density of state goes as energy to the power half. But that would be different depending on how many dimensions you are. Like in 2D, you would see that the density of states is a constant value, while for 1D it goes as energy to the power minus half. So this power or this expressions for density of states is a function of what kind of dispersion relations you have and what kind of dimensions you are in, your system is in. And then what is different from the Fermi gas in this case is that now you have to be very careful in taking into account the epsilon equal to 0 state. In the last case, we did not consider or think much about the fact that if the density of state, so what this tells you is the density of state is 0 when energy equal to 0, but that's not actually true. You can have particles in the zeroth state. In the Fermi case, we were not very concerned about that because we know that for fermions, either the number of particles in a particular state can be 0 or 1. So that does not change or does not affect your calculations much. But now when you are in the Bose gas, when you're talking about Bose gases, there you can have all the particles can also be in the zeroth state. That is also physically possible. So that means you cannot ignore the case when energy is equal to zero. You have to explicitly take that into account. So what is done here is that you take epsilon equal to zero case outside the integral and you write it, like include it explicitly. That's how the expression for pressure and the number of particles per unit volume, it has changed now. You have this extra terms that come in because of the case when energy is equal to zero. Okay, and you see that now, depending on whether you are in the classical limit or in the quantum limit, your the importance of this term would change, right? So when z is much, much smaller than 1, that is when you're in the classical limit, you can ignore this term, right? But then as it increases, or as it tends towards 1, this term becomes very dominant. And then you have a term like uh, n naught by v, where n naught could be the number of particles in the ground state, right? So from there, what you can now do is you can define a Bose-Einstein function, which is given by this integral here. That's actually a series. And then you can write the pressure or the number of particles in terms of this Bose-Einstein function, okay? And this is the thermal wavelength. And you can also use the same expressions to find the internal energy by using the relation of how it relates to the partition function, okay? And that gives you this expression for the internal energy. And what in a way is important is that now if you look at this term, n minus n naught is actually the number of particles in the excited state. If n naught is the number of particles in the ground state, n is the total number of particles. So n minus n naught is the number of particles in the excited state, okay? And that in a way, so this expression in a way sets a limit to the number of particles that can be present in the excited state. So because your Bose-Einstein function is a bounded function, so when z is set to 1, this achieves the maximum value that is given by the zeta functions, right? So that means when z is equal to 1, this term goes to its maximum value given by zeta of 3 by 2, or and if you put that value, that sets a maximum limit to the number of particles that can be present in all the excited states. So that means now if your number of particles, total number of particles, if it is less than any, all particles will be distributed over the excited states. But once the number of particles becomes greater than NE, where NE is the maximum limit that your maximum limit to the number of particles in the excited state, what happens? So all the extra particles would then go to the ground state, right? So this is your, when n is greater than any, this is the total number of particles in the excited state. N minus this term would give you the number of particles in the ground state given as n naught. And here what we will see is that z it gradually tends towards 1. So in all these cases, when n is greater than any, your z is practically close to 1. So what happens here is that now this tells you that when your number of particle is beyond this maximum limit, what will happen? Particles will start coming into the ground state, okay? And that sets in the condition for the Bose-Einstein condensation, okay? So now if you keep N and V constant and vary temperature, this will tell you that beyond or below a certain critical temperature, your condensation will start. And as you will go towards the zero energy, zero temperature, you will have large number of particles or almost all particles coming towards the energy equal to zero state. And that is the Bose-Einstein condensation that one sees in Bose gases. So that means Tc is a characteristic temperature that depends on particle mass and the number density. And now if your temperature is less than Tc, your system can be looked at as a mixture of two phases. One is a normal phase consisting of any number of particles over excited states. And then there is a condensed phase that consists of n naught number of particles accumulated in the ground state energy equal to zero, right? So once you have this expression, you can tell that given some value of n and v, whether condensation can happen or not, right? And below the critical temperature or beyond the critical temperature, this is how your number of particles in the excited state or the ground state varies, okay? And same goes for the value of z. So you see that below the critical temperature, your value of z is always 1, and then it gradually decreases. Okay. Again, here you would see that so n lambda q gives a measure of whether you are in the classical limit or in the quantum limit. So when t is less than tc, you can replace the Bose-Einstein function by the zeta function. And then this will tell you that now the pressure is proportional to t to the power 5 by 2, right? And this is how your pressure would look like at the critical point. While when the temperature is greater than Tc, you have this Bose-Einstein functions now, okay? And you don't replace it by the zeta function, right? Here you have it uh, as same. So you have G5 by 2, Z by G3 by 2, Z. Now this factors, whether it's 5 by 2 or 3 by 2, depends on what kind of, again, it depends on what kind of dimensions you are talking about, or what is the dispersion relation, or what is the Hamiltonian that you are talking about, right? And you can find the expression for internal energy and use it to find the corresponding expressions for the specific heat below or above the critical temperature. And you would see that at the critical value, the value of specific heat is higher than the classical value, and it gradually dies down towards the classical limit as you increase the temperature. Okay. So then we solved these two important questions which showed that for some dispersion relation where energy is proportional to momentum as k to the power s, okay, a and s are constants, for a given system with dimensions d, Bose-Einstein condensation would occur when any of these conditions would be true. And what is the answer? Would be governed by the fact that any should be defined. And that tells you that d by s should be greater than 1. And if you now check for 3D, you would see that for materialistic particles, that is massive particles, or for massless particles, for both the cases, the d by s value is greater than 1. That comes from the fact that the expression for any should be defined under all conditions. So if you look at the expression for any, that would tell you what should be the value of S, or the power of momentum in the expression for energy, and what should be the dimension, how they should be related for the Bose-Einstein condensation to happen. So this again tells you that for massive bosons, where S is equal to 2, because you have like expression like energy equal to p square by 2m, so S equal to 2, Bose-Einstein condensation can occur when the number of dimensions is greater than 3. So it can happen in 3D, but not in 2D or 1D. While for massless bosons, where S is equal to 1, your Bose-Einstein condensation can happen in 2D and 3D, but not in 1D. So this comes from the same relation that d by s should be greater than 1, that is, the expression for n should be defined, right? So then what we looked at was, this was what we had discussed in the last class, that was about harmonically trapped Bose gas. So here you see that the density of state is no longer proportional to epsilon to the power half, even in 3D, because now your particles are not free, they are harmonically trapped. So what happens is now you find the density of states using this relations here, but which comes from the fact that the energy Ex plus Ey plus Ez should give you the total energy E. And then you put the limits from 0 to infinity, 0 to epsilon, so that you find all the number of states that can lie between 0 to epsilon. Okay. And this is how you get to the density of states, right? And now if you know that ln q is given by this summation here, you can change to the integral given by this expression where ge now is the density of states. So similarly, you can find the integration for the number of particles, and if you do that, this is the expression that you will get. So now you see that this was initially 3 by 2. If you look at the free particles, if I am not mistaken, let me just check once. So yes, right. So you have 3 by 2, right? But now you would have 3. So that means this values would depend on what kind of system you are in, right? So now you have, this is your expression for n. So similarly, as we did in the last case, you can say that the maximum value of n happens when z is equal to 1, and that sets your maximum value of n. And from there, you can find an expression for the critical temperature. So this is the basic way of approaching this kind of questions where you need to find the critical temperature of some system for the Bose-Einstein condensation to happen. And similarly, now for temperatures above Tc, your Ne by N is equal to 1, and this is how you define N. While for T less than Tc, what happens is now your N is greater than Ne, so now particles start coming to the ground state, and then Ne by N is given by this relation here. So this is how the plots look like. You can follow the same concepts of finding the energy and then finding the specific heats. Here you will see that if you find the expression for specific heat at the critical temperature while approaching from Tc plus, that is from higher temperatures, this is the expression that you get. And that does not match with the expression that you get when you approach from the lower temperatures, right? And this tells you that there is a discontinuity in specific heat, as you can see in this plot here. And this is how the discontinuity looks like. Okay. And then finally, we had discussed about the general treatment of Bose gas. So we saw that for some general density of state, which goes as C alpha epsilon to the power alpha minus 1, like for non-relativistic gas in 3D, you can say that your alpha is now 3 by 2, while for 3D harmonic trap, your alpha would be 3, right? And if you do that, you can find you can do this integral and similarly find the expressions. This is a general expression for the number of particles, or you can then use it considering that z tends to 1 for t less than tc. You can replace the Bose-Einstein function by the zeta function, and that would give you an expression for the critical temperature. So this is a general temperature given in terms of this general density of states. And then you can extend it to find the expression for energy, use it to find the expression for the different specific heats. So these are the very general cases. And again, here you can see that when you go to temperatures much larger than the critical temperature, you get the classical limit. So all these things are consistent. So uh, this was how our entire course was executed. So we started with thermodynamics, we spoke about probability, we spoke about ensemble theory and under what conditions, what kind of ensembles are to be used, and how we can use the ensemble theory to find the expression for different thermodynamic variables. And then we went to the probabilistic distribution, where we first discussed and introduced the concept of density metrics. Okay. And then we moved towards the quantum mechanical description, how things change depending on whether the particles are distinguishable or indistinguishable. And then we spoke about depending on whether the particles are bosons or fermions, how does the mean occupation number change? How do they manifest in terms of the different, you can say, in terms of the different thermodynamic variables, right? So you can, the change in mean occupation number is manifested in the change in expression of all the different thermodynamic variables. And we see that we particularly dealt with Bose gas and Fermi gas, and we saw that for Bose gas, beyond a certain temperature or below a certain critical temperature, condensation starts, where particles come into the ground state and they come and accumulate there, right? And this critical temperature, or whether the critical condensation is possible or not, depends on what kind of the dispersion relation we are talking about and what is the dimension of a system. Okay. And that's all. This was a general treatment of Bose gas, which would satisfy all the particular cases depending on what dimensions and what dispersion relations you are dealing with. So that was all for this course. I hope it was helpful for you. So yeah, thank you.